All right, so good night. Welcome to tonight's class. Tonight we're looking at electrochemistry. We're going through the revision for your chemistry exams. Tonight we'll be working 5 electrochemistry questions or electrolysis questions from past papers. Remember that as I project the questions on your screen, feel free to message in your answers as I ask you as we go along, just to compare what are your answers and what are the correct answers. So first question here gives us an introduction that Jack was required to conduct an investigation on the electrolysis of concentrated sodium chloride solution. Identify 2 ions present in the electrolyte and include their state symbols. So there may be more than 2 ions, but the question only asks you for 2. So I'm going to write out all possible answers. I see some of you already start sending through your answers. Remember though that so the question asks you for 2 things. Apart from the ions, you also need to put what are the state symbols. If you had the 2 ions correct, but you did not put in state symbols, then you'll have you will actually lose a mark there, and you'll only get 1 mark out of 2 marks. So this here was concentrated sodium chloride solution. So from this sodium chloride, we will expect to have Na plus ions and Cl minus ions. That's from the sodium chloride. And from the solution meaning that so we had to dissolve it into water, we're going to have H plus and OH minus. All right, so these are the ions. The question also asks us for the state symbols. So actually all of them are going to be aqueous, all right, because this here was a solution. So remember, so this is not a molten, yes, I somebody someone is asking about molten. This is not a molten form of sodium chloride. This is concentrated sodium chloride. So it means that the student Jack took sodium chloride solution, so sodium chloride salt rather, place it in water and make a solution, right? So all the ions present there are in an aqueous state. If Jack will have heat the sodium chloride salt and make it into a liquid, then in the molten form, then we'll have that sodium ions and chloride ions are liquid. All right, good. Part 2. State 2 factors that affect the discharge of an ion in the electrolyte during electrolysis. So there are 3 factors, any 2 of them you can state. So I'm just going to write down all 3 answers, so any 2 you can have. So the first one there, well, I'm just going through the order that we'll have learned in class. Position of ion in electrochemical series. The next is the concentration of the ion in the solution. And third, it can also be the type or the nature of the electrode. All right, so any 2 of these here will give you 2 marks. Part 3 of the question. It asks us here, predict which ions present in the electrolyte will be attracted towards the anode. So let me just go back to the ions so you can get a look at the ions here. So which ions will be attracted to the anode? So remember the anode, we're going to have the anions being attracted to towards the anode. So the answer there is going to be the chloride ions and the hydroxide ions. I see somebody say they will have been writing anions. Well, if you write the word anions, you only get 1 mark, right? You're supposed to state the name of the 2 ions, and then you'll get your 2 marks. Part 4 of the question now asks us write a chemical balance equation for the reaction at the anode. So we first have to decide, okay, that which out of these 2 ions now, both of them are going to be attracted towards the anode, but which one is going to be preferentially discharged? So out of these 2 here, let's make that decision. Which one, chloride ions or the hydroxide ions, will be discharged at the anode? And you can probably tell me the reason why one time. All right, so only the persons who said chloride ions are correct, all right? And why chloride ions is because it's more concentrated. Remember, this here is a concentrated sodium chloride solution, so we expect that the salt, sodium, and chloride ions here are going to be more concentrated. So it is the chloride ions that will be discharged, and reason being that it's more concentrated. The question didn't ask you for that, we're just doing a bit of revision there. So the question asks you for the equation though that is happening at the anode. So for the chloride ions, this is going to be 2 chloride ions minus 2 electrons to give you Cl2 gas. All right, and remember that, so whenever we write in half equations or ionic equations, we must include our state symbols. Because if the equation does not contain state symbols, you will lose 1 mark. Part 5 of the question. It asks us now to write a balance equation for the reaction at the cathode. So we had 2 cations, that's sodium and hydrogen ions. So remember, to at the cathode, basically it's that force rule will be applicable, that is whichever one is lower in the electrochemical series. So it is going to be the hydrogen ion being discharged. Right, so that equation is going to be 2H plus ions plus 2 electrons to give us H2 gas, and this here is aqueous. Part B of the question. Now this is a very simple part. It simply asks us, state whether each of the substances given in the table are classified as conductors or non-conductors. So magnesium ribbon, we have plastic rule, and we also have an aqueous solution of magnesium chloride. So let's go to the first one, magnesium ribbon. Is that conductor or non-conductor? Good, so all those were saying conductor, and that is correct. Good, we go on to plastic wool now. Well, that one is very simple. That is going to be non-conductor. Now, how about the aqueous solution of magnesium chloride? Good, correct, that is going to be a conductor, right? That's an electrolyte. So it is a conductor. All right, so we go on to the second question. This question reads that the applications of electrolysis can be varied. It can be used to extract some metals from their compounds and to protect metals from corrosion. First part asks us, define the term electrolysis. So we went through this the last class. I said that so whenever you're defining electrolysis, there are two main points, right? So ensure that's how you cover both points here. So I'm going to write out the definition, and you can compare your answer to this definition. Yes, so definition here, this is another definition just presenting to you. Passage of an electric current through an electrolyte, that's the first point. And the second there is that it must produce a chemical change. So some of you are using the word decomposition for that chemical change. All right, I see some of you reword it, put in the chemical change at the beginning. Okay, that is good. Still means the same thing, but again, you must have those two points or two parts of the definition to get the full marks. So the first part will be from passage of electric current through an electrolyte, and then the other part producing a chemical change. Part 2 of the question. Describe what happens during the electrolysis of molten sodium chloride and support your answer with relevant balanced ionic equations. So just now we look at the electrolysis of concentrated sodium chloride solution, but now we're talking about electrolysis of molten sodium chloride. So let's talk about the ions present first before we start analyzing or making a judgment about what is going to happen. What are the ions present in this system? In the electrolytic cell, what is present? What ions are present? Good, so we have, some persons are correct, we have sodium plus ions, we have Cl minus ions. Now, will we have H plus and OH? I see some persons are saying, yes, indeed, we're going to have H plus and OH. But if you read there, it is molten sodium chloride. So molten sodium chloride means that we take the solid sodium chloride and we heat it and it becomes a liquid. right? Or we melt sodium chloride. So it is only going to be sodium plus ions, chloride minus ions. So now we can go ahead and talk about what is going to happen during the electrolysis of molten sodium chloride. So at the cathode, which ion is going to be discharged? Good, so we have that the sodium ions discharge. And we can write the equation here one time. Just a you can type in the equation. Also, you can just check on your equation how you're going with that. So obviously, if it's the sodium ions at the cathode, it is going to be the chloride ions discharged at the anode. Good. So I see some of you managed to write the equation for the cathode. I just given the others a chance quickly to type in their equation. All right, so you're correct. Remember again that you must have your state symbols. Some person must know that. So it is going to be sodium with a positive charge. It's liquid plus electron to form sodium, and this sodium is going to be in a liquid state. At the anode, we're going to have 2Cl minus ions, which is in a liquid state, minus 2 electrons to form Cl2 gas. All right, so this is going to give you 4 marks. 1 mark for correctly identifying which ions are going to be preferentially discharged at each of the electrodes. And then we have another set of marks going for your equations here. Someone's asked me if you have to word it. Word it mean what? You write out the word equation, or is that what you're asking me? Oh, if you want, you could have, write out the first part where I write sodium ions are discharged. You can also write that sodium ions are migrate towards the cathode and are discharged. You can write that also. You can even state what is the cathode and that it is the negative electrode. You can even say in your sentence or your description that the anode is the positive electrode which attracts the chloride ions and things like that. So positive electrode, which is the anode, and just put the signs here, positive, and this here is negative. So you can write out that in words. Right, but once you have what is on screen here, then basically you get in your full marks. All right, part B of the question. It says here that aqueous sodium chloride can be electrolyzed using inert electrodes. Discuss the effect that the position of ions in electrochemical series has on the products of this electrolysis. So the first statement we want to make is what is the effect of the position of ions in the electrochemical series in terms of which one is being discharged. We probably talked that earlier already. So is it lower in the series that those ions are going to be discharged, or the ions that are at the top of the series? Good, right? So everybody should understand that or know that by now. So it is ions lower in the electrochemical series are discharged. All right, and discharge together there. Are discharged in preference. All right, so that's the first thing you want to be seeing here. That's all. Whichever ions are lower in the electrochemical series are discharged in preference. So in this aqueous sodium chloride solution, we're going to have sodium chloride ions, sodium ions, chloride ions. So we have hydrogen ions and we have OH minus ions. So we talk about the cations now. Which one is lower out of sodium and hydrogen? Out of sodium and hydrogen, which is lower in the electrochemical series? Good, so it is hydrogen lower. So what will be produced at the cathode? Good, so we expect here, correct, hydrogen gas, for those who are saying that. Hydrogen gas produced. At the anode, which is lower, is it chloride ions or the hydroxide ions? Good, so it's correct, it is going to be the OH minus ions, lower in electrochemical series. So what will be produced? If the OH ions are being discharged? Good, so correct, we have water and O2 gas produced. All right, so when you're making your discussion here, you're showing that because now we have different ions and we have to look at the position of the ions in the electrochemical series, we're going to have different products, and compared to the first instance where we had molten sodium chloride. All right, so the position of electrochemical series will indeed have an effect on what are the products of the electrolysis. So I'm saying for state symbols. Oh, what is a liquid? That's why I didn't write that. It's just that whenever we write the gas, we put that in. All right, so it is H2O, O2 being produced. All right, then. So the next part C of it, deals with one of the applications of electrolysis. So it tells us here that aluminum is made corrosion resistant by anodizing it. Using a label diagram and equations, explain what happens during the anodizing of aluminum. So before I go through the answer with you, you can just tell me quickly what is the process, what is the basic principles of the process of anodizing of aluminum. All right, so I see some persons there saying they can't recall what is basically anodizing. Some persons are making some guesses, but see somebody saying that forming a coating of oxygen on the aluminum. So if you can recall, when we were discussing corrosion of metals, we'd have said that, you know what, that the aluminum doesn't corrode so much as the other metals, simply because there is a layer of aluminum oxide over the aluminum. So during this process, and the introduction tells you that aluminum is made corrosion resistant by this process here. So I have a picture of a note taken from one of the textbooks that we normally use in class here. And it tells us here that we simply anodizing is a method of producing a coating on objects, and that coating is an aluminum oxide coating. So just going through the diagram for you. Let me just change over the color here. Good. So if we notice, for this diagram, or for this process, we take the aluminum, the object to be coated, and we place it at the anode. All right. The cathode, we use an inert cathode, and the electrolyte is a solution that will liberate oxygen during this process here at the anode. So basically, once we use a dilute solution here, if you can recall, the OH ions are going to be lower in the electrochemical series, and in the process, oxygen gas is going to be produced. So this textbook is given an example that we can probably use dilute sulfuric acid. And during this process now, we know that our OH minus ions and the sulfate ions are going to be the anions. And because the OH minus ions are lower in electrochemical series, they're going to be preferentially discharged at the anode. During this process, the OH minus ions are going to produce water and oxygen gas. The oxygen gas is going to react with the aluminum to form an aluminum oxide coating, which is what this process of anodizing is all about. So someone is asking me if this here is electroplating. Remember, so electroplating is, yes, we are coating that object, right? But with electroplating, we're coating a metal with another metal. It can probably be the same metal, but we're coating metal with metal. All right, and during that process of electroplating, we normally place our object to be plated at the cathode and not at the anode. So if you want to plate the copper with something, we will be placing a copper metal at the cathode, right? So that's a big difference there. For electroplating, we place our object to be plated at the cathode. And for anodizing here, we're placing the object to be anodized at the anode. All right, so I think any question more? Any more other questions on this here? All right, so we go there. So we go to another question, question 3 for tonight. And again, the first part asks to define electrolysis. We're not going to be defining electrolysis again, but I just want to show you that more likely in these questions here, you're asked to define the term electrolysis. And if you notice there again, it is for 2 marks. And so it will accommodate the 2 points that we'll have discussed. Now this question here has another application of electrolysis, and it talks about purification of copper. So we look at anodizing just now. Now this question here is based on purification of copper. So let's go on to part 2 of the question. Well, let me read the introduction first of all. Tells us here that The process of electrolysis has a number of useful applications during the purification of copper by electrolysis. Special electrodes are used to give the desired products. First part, the part that we're going to answer now. State the type of anode that is used in the purification of copper. So I'm seeing persons are saying active electrodes. This here is just worth 1 mark. So more likely you will not get that 1 mark. Now, during the purification of copper, it means therefore that we're going to be having some piece of impure copper. So this impure copper is going to be at the anode. So let me just draw the diagram. Let me see if the question will follow up by asking you to draw a diagram. Or then I can just go through the explanation here. All right, so let me just go through the explanation here. For those who probably a bit lost here. So let's just go through a bit of revision here. This longer stroke on the battery, what is that representing? The negative or the positive terminal? Good, so that is a positive. This here is going to be the negative. So which of the electrodes are called the anode and the cathode? The one connected to the negative is called what? So that's this one here that I already drew. What do we call that? Do we call it the cathode or do we call that the anode? Correct, so we call that the cathode, right? So good that you're remembering. So I'm not going to draw the anode as yet. So in this experiment here, purification of copper, both our electrodes are active electrodes. Now, can you recall what happened at the anode during electrolysis when we use active electrode? What did I tell you is going to happen to the anode during electrolysis whenever we're using an active electrode? Good. So I see some persons already saying that it is going to dissolve. So I'm just drawing it like this here to represent good. So this container should have been larger. So the anode here is our impure copper. Our solution that we're using, or the electrolyte that we're using, has to be some copper solution. So probably we're going to be using copper sulfate solution. All right, dilute copper sulfate. So what do we expect to happen in this process here? We expect that the copper, we have copper 2+ ions here. We have hydrogen ions. We also have sulfate, and we have OH minus. So during this process, we expect that the copper 2+ ions are going to be going towards the cathode. All right, so it has been coated, the cathode is going to be coated. At the same time, the copper from the impure copper anode is going to dissolve into the solution, right? That's what we said will happen. And the impure pieces are going to fall somewhere here. All right, so in this process here, we actually collecting back the copper, because as the copper ions from the electrolyte are going towards the cathode, we have copper dissolving back into the electrolyte. Right, so the copper is going to be dissolving here, and at the same time, we have the impure pieces falling at the bottom. All right, so those who have the concise chemistry text, you can probably check page 73, and you can see that there's a label diagram there with a bit of explanation that you can follow through for a little more notes, those who want some more notes. Part B of the question. It tells us here that the figure depicts the apparatus that is used to electrolyze a sample of molten lead-2 bromide. It asks you a simple question. Which of the electrodes, electrode 1 or electrode 2, is the cathode? So that's a simple question, right? And we just talked that through. You're supposed to be able to answer that quickly. So that is going to be electrode 2, right? So that you're correct there. Next part asks us, write the formula of the ion that migrates towards the anode. So this here is a molten lead-2 bromide. So molten means that it's only going to be lead-2. So that's Pb2 plus and bromide, Br minus. So which one of the ions is going to go towards the anode? Good. So you're correct there. It is going to be the bromide ion. The third part there now asks us, write a balanced ionic equation for the reaction occurring at the cathode. So at the cathode, we know that it is going to be the lead-2 plus ions. So this is going to be Pb2 plus 2 electrons to give you Pb. All right, this will have been in liquid form. It is molten. And here we're going to have solid lead. So we went through these equations already, so most of you should be able to write that. So part 4 of the question gives us a bit of calculation. So I'm going to give you a chance, 2 minutes, attempt the question and tell me what is your answer. And then we're going to work it together to see if you're correct. All right, so I see a couple of persons are finished already, and the rest of you, let me know which part are you at right now. All right, so most persons are those who are not finished at the last part, so hurry up. All right, so let's work the question together. So the first thing we're doing is that we're finding the quantity, so that is going to be Q is equal to IT. So current is given as 5 amperes multiplied by the time is given in minutes, so we need to convert the minutes to seconds. So this is going to be 5 times 60 seconds, which is equal to 1500 coulombs. All right, so the next step we do is we find the number of Faradays. So number of Faradays is equal to 1500 divided by 96,500, which is equal to 0.0155 Faradays. Now from the equation, we get that 2 Faradays is equal to 1 mole of lead. In our calculations, though, this is from the equation. So from our calculation, though, we got that we have U 0.0155 Faradays is equal to X mole lead. So therefore, X will equal to 0.0155 divided by 2, which is equal to 7.75 times 10 to the minus 3. So now we know that's how 7.75 times 10 to the minus 3 moles of lead deposited. So 1 mole of lead is given as 207 grams. So therefore 7.75 times 10 to the minus 3 moles of lead will equal to 207 grams multiplied by 7.75 times 10 to the minus 3. And this will work out to be 1.6 grams. All right, so the answer there is 1.6 grams. So I see some of you managed to get the answer eventually. Some of you will have sent in some answers that you will have recognized that that are incorrect, and then you probably hurry up and do back your corrections. All right, so part C of the same question, it tells us that two experiments were set up as shown in the figure there. In one container, we had magnesium sulfate, and in another, we had copper sulfate solution. Now, in both solutions, zinc rods were placed inside, or a zinc rod rather, was placed in each of the solution. The observation for the experiments was that in the first experiment, there was no visible change. And in the second experiment, a brown solid settled to the bottom of the container. So the question is asking you, explain your observations from both of these experiments. So let me hear your thoughts here quickly before I start discussing the answer here. Why is it that in the first experiment, there is no visible change? And in the second, we have a brown solid settling to the bottom. All right, so I see somebody sending the answer, correct? Remember that you'll have to, I see somebody else send the answer. Remember you have to give me an answer for both of the experiments. So what we have to do is to recall the order of these metals here in the reactivity series. So in the order from top, we're going to have magnesium, zinc, and then we have copper. All right, so what this is telling us that magnesium is more reactive than zinc is more reactive than copper. So in the first experiment here, zinc is lower in the reactivity series than magnesium. So zinc cannot displace magnesium. All right, so that is why we're going to have no visible change. So this reaction here, magnesium sulfate rather, plus zinc is going to have no reaction. And simply because zinc cannot displace magnesium. But in the other experiment, where we have zinc plus copper sulfate solution, zinc is higher than copper in the reactivity series, so therefore zinc can displace copper and is going to form zinc sulfate plus copper, and that is the brown solid. The brown solid that the observation part is telling us. So that brown solid is copper being displaced by zinc in the copper 2 sulfate solution. All right, so this experiment was based on the reactivity series. So it is not an electrolysis, but it was part of the question that we're working. So I just added in and we just go through. So even if it's not coming for your paper 2, it may come for your paper 1. All right, so we go on to question 4. So question 4 shows it starts out by showing a simplified diagram of the apparatus used for the electrolysis of aqueous copper 2 sulfate using platinum electrodes. First part asks us, deduce the oxidation state of sulfur in copper sulfate. So I'm just going to work that out quickly. So we have copper, sulfur, and the oxygen in copper sulfate. So the question is asking us what is the oxidation state of the sulfur. So we're going to call that X. Copper, we know it is +2, and oxygen, we know it's -2. So working that out, this is going to be like an equation of +2 plus X plus, let me just put these in brackets so you can follow easier. So the +2 was from the copper, The X is from sulfur, and this is going to be minus 2 times 4, and that should be equal to 0. So solve for X and tell me what is the value of X. So X is going to be the oxidation state of sulfur. All right, so I see most of you finish up this. That was a simple thing to work through. So most of you are telling me it is 6. I see some persons telling me it is minus 6. So it is not minus 6. That's definitely incorrect, all right? Because this will work out to be x minus 6 is equal to 0. So therefore, x is going to equal to 6. However, when we write in oxidation state, though, we either put we have to put a sign in front. So we either put it a minus 6 or plus 6. In this case, it is going to be plus 6. Right, so the oxidation state of the sulfur in copper sulfate will be plus 6. Part B of the question. So we went through a bit of this already. And it says here that at the anode, the hydroxide ions are discharged in preference to the sulfate ions. State a reason for this. So most of you should be able to tell me very quickly now. In the copper sulfate solution, we're going to have sulfate ions and we're going to have hydroxide ions. So the question is telling us that the hydroxide ions are going to be in preference to the sulfate ions. Why is it so? And it is correct. It is that because it is lower in the electrochemical series. Any other answer is incorrect, right? Write a balanced equation for the reaction of the anode. Well, again, we have been doing that a lot recently in our revision. So I'm just going to write that out. 4OH minus 4 electrons to give you 2H2O liquid plus O2 minus gas. Someone is asking, no, do not write ECS. I'm just writing it shorthand because of the time and things like that. What you spell out electrochemical series. Part D of the question. Says there from the equation written above, state whether the reaction is an oxidation or a reduction reaction. And just for 1 mark, give an explanation for your answer. So you're not expected to be writing too much. So first of all, let's try to agree with that. Is that an oxidation reaction or is it a reduction reaction? And then you can just tell me why you're saying that. Good, so I see most of you telling me it is oxidation. I'm waiting the explanation. So correct, this is oxidation. And if you can recall the mnemonic, oil rig. All right, this is for electrons. That oxidation is loss of electrons, reduction is gain of electrons. So the reason being is because there is a loss of electrons. Part E of the question. State 2 changes that occur in the electrolyte. So let me just sketch the diagram at the bottom, what's happening in electrolyte. So in the electrolyte, this is a container. We had copper 2 plus from the copper, sulfate 2 minus, we had hydroxide, and we also had H plus. So the first thing is that is going to happen, we know that all the copper 2 plus ions are going to be converted to copper solid, all right? So if copper 2 plus ions are being removed from the solution, in terms of the color, what do we expect to happen? Well, I'm certain you can recall that the blue color of copper sulfate is because of the presence of the copper 2 plus ions. So if we are taking out copper 2 plus ions in the formation of the copper solid, what will happen to the color of the solution? Good, correct. We expect it to get be less blue, or the blue color is going to fade. All right. So first point you can make is that blue color of electrolyte fades. Right. So what's the next one now? So that is one we talk about. What will be another change to the electrolyte during this process? So I see somebody say hydrogen gas. I'm not too sure. Remember that we have to talk about the electrolyte. What is happening to the electrolyte? All right. So so persons who are talking about the observations, remember that that is not what's happening to the electrolyte, right? That is observation at the electrodes. So what is going to happen is that we expect that the electrolyte becomes more acidic. All right. So why is that so? Remember that so during this process here, we are removing copper 2 plus ions, and at the anode, which ion are we removing? All right, I see somebody say copper. It's not copper. Copper is at the cathode. So at the anode, we are removing the hydroxide. Let me just circle that in red. So we're removing hydroxide. So we notice that H plus and SO4 2 minus remains. Is that relating anything to you? H plus, SO4 minus? Good. So some of you are recognizing it. It is sulfuric acid, right? So once the H plus ions and the SO4 minus ions are left behind, we expect that this solution here is going to become more acidic. All right. So one thing I want you to be conscious about when you're answering or when you're practicing your electrolytic cells, what is going to happen at the cathode, what is going to happen at the anode. Also go through what is going to happen to the electrolyte, right? To try to figure out what's happening to the electrolyte. Because in an exam, you can be asked, as this question is showing you, that you can be asked what is will happen at the electrolyte. So part F of the question is one similar to the one that we worked just now. So let's hope that this time everybody gets it correct and at a faster pace. So giving you 2 minutes this time. I can't recall how much minutes I gave you just now, but it was longer than 2 minutes. So 2 minutes this time, and then I expect you to finish up. All right, so let's go through. I see most of you are finished. So let's work it together. So again, we go through the process. We find Q, and that's going to equal to I is given as 5 amperes multiplied by time is given as half of an hour. All right, so that's actually 30 minutes. So we can convert the 30 minutes to seconds. Which will give us an answer of 9,000 coulombs. So we find number of Faradays next. Number of Faradays is equal to 9,000 divided by 96,500, which is equal to 0.093, let's go 33 Faradays. So the equation, the question did not give equation. So for those who are asking if you normally get the equation in exam, well, this one here is showing you that you need to write your own equations at times. So this is going to be copper 2 plus 2 electrons to give us copper. So from here we can see that our 2 Faradays is equal to 1 mole of copper. You know how we get the 2 Faradays? It is because we have 2 electrons and we get 1 mole of copper because there's 1 in front of the copper. So this is from the equation, and that's how 2 Faradays is equal to 1 mole. So therefore 0.0933 Faradays is equal to x mole. So we're solving for x. So therefore x is equal to 0.0933 divided by 2, which is equal to 0.0465. And I'm going to keep the entire number, 0.04665. So from this here, we can see that 0.04665 665 moles of copper was deposited. Question gives us that 1 mole of copper is equal to 64 grams. So therefore this amount, 0.665 moles, will equal to 64 grams multiplied that by the same number, 0.04665, and that is equal to approximately 3 grams. Or sorry about that. Yes, approximately 3 grams. So we'll have an answer that 3 grams of copper was deposited. Good. So I see most of you got that answer. All right. So part G of the question, this question actually had up to part G. Says here, indicate below how the apparatus in figure 3, where I provide the apparatus on screen here, can be modified to obtain pure copper from impure copper. So we just look at that, I think it was the previous question. So let me see if you can recall. What should happen at the anode instead of the platinum cathode on the anodes? What should be placed at the anode? What should be placed at the cathode? And what should be the electrolyte? Well, it tells us here that if no modification is needed, no change is needed, we just write no modification required. Good. So the anode, I see some persons incorrect. We should put the impure copper here. Copper, or use impure copper. What should happen at the cathode? Any changes, or are we leaving the cathode as it is? All right, so those who are saying pure copper, you're correct. I'm going to tell the cathode should be pure copper because we are putting the copper back together. You don't want to put copper on top of the platinum, and then how are you going to get back the copper, right? So usually you have pure copper there. And the electrolyte should be a copper salt, and so we see that we have a copper salt there already. So we're going to say no modification required. All right, because copper sulfate is there already. Don't need to write back copper sulfate. All right, so last question for the evening. So this question here talks about identifying substances as either conductors or non-conductors. So it tells us here that some students in a chemistry class were asked to classify some substances, and they're given some apparatus. They're given a bulb, source of power, 2 graphite rods, connecting wire. And they're also provided with the following substances for testing: a zinc metal, aqueous bromide solution, potassium bromide, sorry, solution of bromine in carbon tetrachloride, and solid potassium bromide. So they had to carry out an experiment and complete the table. So the first part asks us, draw a fully labeled generalized diagram to show how you can use the materials to conduct the experiment to determine whether these substances are conductors or non-conductors. So I have the diagram already on screen here. Now, based on what apparatus was given, we were given a bulb, source of power, 2 graphite rods, and connecting wires. We'll be using one that is similar to circuit 2. All right, so you will have your power source. You just modify this diagram here. I'm just showing you 2 diagrams one in which we can test a solid and one we can test a liquid. But this question asks us to draw a generalized diagram that can test either solid or liquid. So we'll have our power source. Question then asks us about a switch. So you can take out a switch and draw in, instead of an ammeter, we draw in a bulb. All right, and we draw our two graphite rods. So that will have been your generalized diagram that you'll be using. So if you're using a solid, all we have to do is just to touch the two solids here, and we'll look and see what is going to happen at the bulb. And if you have a liquid, you're using as what this diagram is showing. We use a beaker with this solution inside. So that will be for your 2 marks to draw your generalized diagram. All right, so that should be relatively simple. Part 2 and part 3 ask us to complete the table. One time they're asking to write in what should be the observation, and another time they're asking you to give an explanation for the observation. So let's just go back to the table. And remember, that's what we have in this circuit here. We have a bulb and we have battery wires, right? So more likely you're saying that if bulb is going to light or bulb does not light. So zinc metal. Let's go through all the observations and then we talk about the explanation at last. Go to zinc metal, we know that a bulb lights. Aqueous potassium bromide. The second one. So I'm seeing that some persons are thinking that the aqueous potassium bromide will not light. Note here, this is an ionic salt. All right, so the explanation is going to tell us just now that, oh, indeed, that the bulb will light also. All right, so bulb lights again. Solution of bromine in carbon tetrachloride. Now, even though this is a solution, all right, we have here covalent compounds, right? So bulb will not light in this case. And likewise, the solid potassium bromide, the bulb will not light again. So let's talk about the reasons. So you can put numbers, probably this is 1, 2, 3, 4, because sometimes when you're typing, other persons are typing in the chat and I'm not gathering why, which answer are you really telling me about. So give an explanation of each of your observation, and let me see whether if you're correct or you're not going on the correct track here. So zinc metal bulb is going to light. Why is it that the zinc metal is going to cause the bulb to light? All right, so we worked a question like this here recently. The answer there is going to be that there are free electrons present. All right, indeed, some persons are saying that zinc metal is a conductor and things like that, but what about conductors is that they have, well, metal conductors that is, they have free electrons present. Aqueous potassium bromide, in this case here, we have free ions present. All right, and in the other 2 cases, there are no free ions present. So in the case of number 3, which is solution of bromine in carbon tetrachloride, those there are covalent compounds. So we do not expect to have ions present. And the last one there, potassium bromide, because it is in its solid state, there are no free ions present. If it was in a solution, which is number 2, or if it was in a molten state. Someone is asking if it's a paper 2. Yes, it is. It's a paper 2 question, and that I'm working here all the time. Actually, all the questions tonight are paper 2 questions. All right, so we okay with this part here. Part B of the question. Well, the definition here, you just talk through the definition. Define electrolysis. We defined that already. Cathode, I'll have asked you already, but in your definition, whenever you're defining the cathode or anode, whichever one you're defining, this question is asking for cathode, you can simply state the charge of the electrode or which terminal is it connected to get your mark. So let's talk about the charge of the cathode or which terminal. Or also you can probably say which ions are attracted to it, which is also a proper definition. But in terms of definition, in terms of charge, we can say that this is the negative electrode, or it is connected to the negative terminal of the battery. The electrode that is connected to the negative terminal. Well, we went through the electrolysis definition several times already. So you're going to work on part 2 of part B, and then we close off for the evening. So let's see if you earn your 3 marks for that part. Okay, so most of you are finished, so let's work it together. So again, first part, it's becoming routine now, but I know some person is still missing some steps. So we're going through together. Q is equal to IT. We're using the formula. This formula here, I is given as 3 amperes. So that's 3 amperes multiplied by time is given in minutes. So we need to convert the minutes to seconds. So this is going to be 10 times 60 seconds. So that's equal to 1800 coulombs. The next number of Faradays is equal to 1800 divided by 96,500. And that will equal to 0.0187 Faradays. So the equation again is not given, so you write to the equation, but by now you should be able to do this very easily. So from this equation, we have that 2 Faradays is equal to 1 mole of copper. So therefore 0.0187 Faradays is equal to X mole copper. So X is equal to 0.0187 divided by 2. Which is equal to 9.35 times 10 to the minus 3. So from here we can see that 9.35 times 10 to the minus 3 moles of copper deposited. So 1 mole of copper from the question tells us that That's equal to 64 grams. So therefore 9.35 times 10 to the minus 3 moles is equal to 64 grams multiplied by 9.35 times 10 to the minus 3, which is equal to 0.6 grams. All right, so mass of copper deposited is equal to 0.6 grams. I see several of you getting that answer. All right, so remember that for those who had some difficulties with the calculations, to review the video I sent you that I worked with the grade 10 students last night. Go through the questions and attempt the questions and then compare your answers and make sure that you can manage to perform the calculations, because there are some of them that you need to calculate volume of gas also. All right, so any questions before I close up? Comments, queries? All right, so no question here. Let me just